A numeric sequence is a string of numbers that follows a certain pattern, like this, and we have a definition of the geometric sequence. Geometric sequence is a numeric sequence where each term can be found by multiplying the preceding term by a common ratio. So we can see in this example here that if I multiply 2 with 2, I get 4. If I multiply 4 with 2, I don't get 6. So this is not a geometric sequence. Had I written 2, 4, 8, 16, you would see that here I multiply with 2, here I multiply with 2, and here I multiply with 2 to get 16. So this example is a geometric sequence, whereas this one here is what we call an arithmetic sequence. When we have that 2 times 2 is 4 and 4 times 2 is 8, we can also frame these as 4 divided by 2 is 2 and 8 divided by 4 is 2. And what we see here then is we have a way of identifying a geometric sequence. If we take one term and divide it on the previous term, and we get the same number, then we have a geometric sequence. And this number that is the same is called the common ratio. And we use R for short. If we examine our example here, where the first term is 2, and then 4, and then 8, and then 16, then we may use U1 for the first term, U2 for the second term, U3 for the third term, and U4 for the fourth term. If we establish that the common ratio here is 2, the second term here is 2 multiplied with the common ratio, which is R, which is really U1, the first term, multiplied with the common ratio. Now 8 is the second term, 4, multiplied with the common ratio. But that again means that 8 is U2, the second term, multiplied with common ratio. But we've already seen that instead of U2, we could write U1 multiplied with R, and then we have to multiply with R2 to keep the equal sign. 16 is equal to 8 times 2, or U3 multiplied with the common ratio R, which is the same as the first term multiplied with R, that's the same as U3, and then we have to multiply with R one more time. So we can see here that this part here is the same as U3. That's what we've written in the previous line over here. Now, if I write a new line here, U5, it's going to be 32. 32 is the fifth term. It's going to be 16 times 2 equal to U4 multiplied with R, which is again U1 multiplied with r, multiplied with r, multiplied with r, multiplied with r. And it's getting tiresome with all these r's, so we could just shorten this to u1 multiplied with r to the power of 4. So r times r times r times r, that's r to the power of 4. Is it possible to generalize this for a nth term? So the nth term in this number sequence, well, we don't have an actual number for that then, but that number would be the first term multiplied with r, but how many times? In the previous row, we saw that for u5, we had to put the r, the common ratio, to the power of 4. So one less than the term number. And you would do the same for u4. Here we have r to the power of 3, so it's one less than the term number. So that would work out for the general form of this as well, that we can write n minus 1. And that's the general formula for finding the nth term of a geometric sequence. There are two things we need to know. We need to know the first term, and we also need to know the common ratio. And if you have the first few numbers of a geometric sequence, you're usually, you know what the first term is, and you can find the common ratio by dividing one term with the previous term. So once you do that, you're able to find any number in that sequence if you know which number in the line you're looking for. Now let's look at one example. A marrow plant is 0.5 meters long. Every week it grows by 20%. So it starts by being 0.5 meters long, and the next week it's 20% longer, which should make it 0.6 meters long. And the third week it's going to be 0.72 meters long. So this is U1, this is U2, and this is U3. So we have the first three terms, and the last one is just for a check really, but if we wanted to find the common ratio here, common ratio, we would take 0.6 and divide it by 0.5. Now, dividing by 1/2 would be equal to multiplying with 2. So we have 0.6 times 2 equals 1.2. So this is our common ratio. And you may actually recognize this as what we know as growth factor. If you know that something increases 20%, you can multiply with 1.20. So this is really the same thing. Now, we have established that U1 is 0.5, our common ratio is 1.2, and task B here asks us to calculate how long the plant is after 12 weeks, which really means that well, we have to think a little here. The first term is 0.5, and after 1 week it's 0.6. So after 1 week we have the second term. So after 12 weeks we don't have the 12th term, but that would be the 13th term. Now you can check that if you're not quite sure, but I'm pretty sure. So U13, we take the first term and we multiply that with the common ratio to the power of 13 minus 1. So now we're just using the formula that we found before. And this would be 0.5 times 1.2 to the power of 12, which gives us a length of 4.46 meters after 12 weeks. Now, question C, comment on the predicted length of the marrow after 1 year. We are looking for the 53rd term after 52 weeks. The first term is 0.5. We will multiply that with 1.2, which is the common ratio, to the power of 53 minus 1. That's the power of 52. And that gives us 6,552 meters. And you're asked to comment on the predicted length, and it seems a bit unlikely that a plant is going to grow to 6 kilometers. So we can't really trust that these sequences in real life, that they're going to go on for infinity. So there are other factors that would limit the growth. But that's one example of how we can use this formula to find any term in the sequence that we want.